All right, everyone. Welcome to the Physics Club. Today we have Professor Andrea Damascelli from the University of British Columbia and the Quantum Matter Institute. A little bit about his bio. He received his PhD from the University of Groningen in '99, did the postdoc at Stanford, where he learned a lot of angle resolved photon emission techniques, and has been a professor at the University of British Columbia since 2002. So he's a world expert in the study of quantum materials, especially using, as I mentioned, angle resolved photon emission techniques, but also time resolved photon probes. And during his time at UBC, he spearheaded a large expansion of the quantum materials group. He oversaw the creation of the UBC Max Planck Tokyo Center and the Stuart Blossom Quantum Matter Institutes. So we brought him today because he has a wide knowledge of experimental condensed matter and solid state physics. And so he's come to share some of the vision that he developed at UBC throughout the years. He's received numerous awards, too many to list. So should add also that he's visiting today and tomorrow. Today's talk is aimed for a broader audience, and tomorrow he's going to present a more technical seminar talk at 1 p.m. in Bacton CO31, talking about probing condensate coherence with time-resolved ARPAs from superconductors to excitonic insulators. So thank you, Andrea, for coming to New Haven, and please go ahead. We'll look forward to the talk.
Thank you. And thanks, Eduardo. Thanks, Karsten, for the invitation, the opportunity to be here, telling us about some of our research. Apology, my voice is going down a little bit, too much talking today. So the idea is, to give you a little bit of an overview of what we do at QMI.
It's the microphone on your laptop.
Echo, yeah.
Speaker on the laptop.
Oh, maybe it's getting remove the volume here.
Okay, now we're sharing again. Where is it? Are you able to find again where was the?
I think you just need to go in your presentation
Again?
Can you speak now?
So how is it? Is it better? Yeah. That is better. But now, how do we go back to that problem that we had before? So. Wait, so maybe first I should go to this. And then, yeah? No.
I think you need to share on the Zoom.
Okay, try that. Yeah, we are still in presentation mode on the other side. I think we have to call Jen again. She did it, so.
Okay.
You can go to display settings and duplicate display.
Yeah. Over here. Duplicate special.
Wow.
Right.
Thank you. Okay, sorry for the challenge there. Even I was saying my voice is dying off a little bit, so but please bear with me and the presentation challenges.
Good.
Are you able to remove it? You can go and remove the.
No.
Yeah. Well, you can minimize it. You can do. Yeah, hide video panel. Yeah.
Go. Hide floating meeting.
Yeah. Okay.
Okay. So the plan is to give you a little bit of a broad view of what we do at QMI. I will take in particular one theme to concentrate on. So all I'm showing is work done under the the aegis of the institute at UBC, but also the International Max Planck Center we have there at UBC, which brings together Max Planck Society, UBC, and University of Tokyo. No, this one doesn't work anymore. Well, This is used to work well. Something has happened again.
This will be from the screen. Right now.
Okay. So here is a very brief history of the Institute. We were started and funded in 2010 at UBC. In 2015, we received a major grant from the Canadian federal government, so-called Canada First Research Excellence Fund. The program we submitted is for quantum materials and future technology, so really bridging the fundamental science that we were strong in at that time with translation and applications. The funding was of the order of 66 million from the government plus 20 from UBC, and UBC also put in a new building for this operation. The mission, you can see it here, and it's basically in a nutshell what is said there, is really going from fundamental work, discovery on quantum materials, design and fabrication of quantum materials, all the way to devices that may be significant for applications. Canada is big now, what is called the National Quantum Strategy, so that's a big push from the government side. But of course, in addition to research and translation, training is a major aspect of this whole operation. Now, in terms of why the need for an institute, I think I like to use this very simple image. This is an experiment. It is the result of a photoionization microscopy experiment done in the Netherlands a few years ago. And what you're observing is basically the nodal structure of a radial wave function for a hydrogen atom. So this is an interference image of a single electron, if you like, a single electronic state for the hydrogen problem, and you can, image what you can calculate very well from quantum mechanics. This is, of course, an experiment that is very challenging. It took a while to realize, but in terms of what you see what you already know. Now, the challenge, of course, is that as soon as you put two electrons into this problem, things change. They change at the theoretical side, making things much more complicated. And it is exactly the kind of challenge we're facing when we look at materials. We are looking at a system where you have a lattice, with whatever that is you're dealing with. This is basically graphite. We're going to see some of that later in the experiment. But the key is now all of the electrons. So in this rendering, all of those electrons propagating through the lattice, interacting with the lattice, and interacting with each other. And of course, you're going from a single electron of a hydrogen problem into the 10 to 23. And as soon as the interaction that's strong, that's when you get the interesting physics. But that's also when the challenge arises in the description. And so that's where the institute comes in. The institute will have three major components: physics, chemistry, and electrical engineering, really going from the fundamental, the big material effort in the devices. And as we have expanded, we expanded from 12 to 26 groups, so 26 faculty members, all under one roof. And then we have seen a large expansion also at the student and postdoctoral level, about 200 altogether. And what is special now, allowed by this funding, was the ability of hiring and retaining scientific and technical staff. So really professional scientific and technical staff working at the boundaries between the different groups. If you look at the people, here is a list of the 26 faculties. Again, color scheme shows you, the different fields. Physics is the dominant one, but certainly now we have a large contingent of chemists, 4 chemists and some join upon it, chemists and physicists, as well as 3 electrical engineers who have come on board in the recent years, really helping us in that effort of translating from fundamental to translational efforts. Here is now the outline of the talk. That's basically the story I'd like to tell you. I'd like to tell you a story about superconductivity, high temperature superconductivity, the way that this has happened at UBC. I'd like to start from the past. The past has really been about the discovery of high temperature superconductors and how the UBC team has come in and looked at this problem, both in terms of growing materials and using them to look at the pairing symmetry of this system and the phase diagram of this class of materials. We'll then move on to the present. Present is really summarized by the new twist and superconductivity. So certainly twisted bilayer graphene is one area. What we are now pushing at UBC, and really from an idea that was born out of UBC QMI, is the idea of twisted cuprates, so twisted high temperature superconductors. And finally, when it comes to the future, I like to show a little bit the ultra-fast time-resolved spectroscopies that tomorrow I'll talk about in more detail. How can we use new tools to really look at really the many-body nature of these materials? So really probing the many-body wave functions and probe the overall coherence of this condensate, and so really the interactions directly. And so that's what I will do tomorrow. and a little bit today just to give you a flavor. So let me start from the past and the basis of this. And please stop me anytime if you have any question. The past, of course, starts off when it comes to high TCs in 1986, discovery of superconductivity at very high temperature. Here you see resistance versus temperature, a decrease of resistance with temperature as you expect in a normal metal, and then suddenly a drop to zero resistance. And a drop that takes place at very high temperature, eventually this temperature will be into the 100 Kelvin range, and of course was capturing the imagination of of society. And here is the cover of Time magazine at that time, referring to the superconducting revolution. In terms of fundamental science, this of course had to do with understanding where such a mechanism and phenomena would come from. The entity that carries superconductivity is no longer a single electron, is now a pair of electrons forming a Cooper pair, forming a bound state. Basically, the two electrons which would naturally repel each other are now bound in a pair which has total momentum of zero, so the two particles moving with opposite momenta, and spin singlet in this particular case. And so the big question is, what is the nature, what is the symmetry of the pairing? So that's the next step. And the next step back in the days was to discuss and resolve whether these superconductors are a new kind. So the conventional, more typical kind of superconductivity is so-called S-wave, where that pairing is fully isotropic in space. But the alternative proposal would be that perhaps in this case we're looking at a gap which is D-wave, or a pairing which is D-wave in nature, where you have regions with very strong pairing into the materials. These are actually the direction where the copper-oxygen bonds are ordered into or aligned in the material, and directions where instead the pairing goes to zero. This is where the node, so the zero in the pairing amplitude, is located. And interestingly, because the order parameter is a complex term, the phase would also change going from one side to the other. So these were the two different proposals. And so then the UBC group set out to do an experiment to really probe that. And so the UBC group at that time is represented by these three gentlemen: Walter Hardy, who now retired, Doug Bond, who is still in the UBC QMI team, and Rasheen Liang, who also recently retired. And what they were after were growing this high purity crystal. This is yttrium, barium, copper oxide. So really their effort was grow the most, the purest samples of this material to do a very specific experiment. The experiment had to do with measuring the microwave penetration depth in the material and be able to distinguish between a pairing or an interaction in this system, having a node or not having a node. And so basically as a function of temperature, seeing whether you could detect a linear behavior or an activated behavior for an S-wave gap isotropic. And so they were able to show in this 93 paper that indeed the behavior is consistent with the presence of nodes in the order parameter. And in order to be able to do that, growing the best possible crystal was a key. Otherwise, impurities would have masked the behavior and made the experiment impossible. This was the beginning of a big effort for UBC, effort that then resulted in these samples being distributed all over the world for all possible experiments. So really, if you look at numbers, they fuel hundreds of papers over the last few years, and received tens of thousands of citations for this specific work. And this is really what put UBC on the map as far as this kind of work. Now, the next step was to, really go and look into not just the pairing symmetry, but also look at the phase diagram of this material. And this in itself is already very surprising. And what you see here is a doping and a temperature axis. Doping means that you can change the number of carriers in this solid just by, for instance, in this particular case of the yttrium, barium, copper oxide, by changing the amount of oxygen. It can be done after the growth. You grow your sample, and then annealing at some condition in some atmosphere, you can change the oxygen content, and you move a number of carriers into this solid this way. And here you find a superconducting dome with temperature approaching the 100 Kelvin. Now, what is surprising is a low doping level, you don't find a metal, which usually would be what you expect as an adjacent phase, but you actually find an insulator, and is actually magnetic with an antiphonetic order for the spin in the copper oxygen plane. So just the exam itself was a big surprise. So the next step was then to understand, really what is the electronic structure underlying this phase diagram, and which then eventually is the one from which superconductivity emerges. And so now we start looking at how to describe the system, and that's where people like me or Eduardo come in, really looking at the detail of the electronic structure. In an atom, you have discrete levels. As you start going towards the molecule, you form some hybridization and some molecular levels. In the solid, of course, the hybridization is strong, and this level evolve into bands. And these bands now come with a new quantum number, which is momentum. It's basically the directional propagation of the electron, and the relation between the directional propagation and the energy of the electron. So this is your band dispersion, which really is critical here, because you're going to feel this energy diagram with electrons up to the point when you run out of electrons. And this is called the Fermi surface. So when we talk about superconductivity, well, everything has to do with the interaction of the electrons at the Fermi surface. Those are the ones that will form the Cooper pairs and will give you superconductivity. So back in the 90s, a lot of effort has been put in developing this technique, angle resolved photon emission spectroscopy, which is what I still do today. And the idea is shining light on a sample in vacuum, removing electron from the sample through photoelectric effect, capturing them with an electron analyzer. It's basically a very large and high resolution capacitor that at the end of it will give you an image that discriminates between electrons based on their kinetic energy and direction of motion. So that's basically the image you measure here. And really, you're measuring the kinetic energy, and direction of motion means projections of that momentum in vacuum. And using simple conservation laws, you can now, knowing the photon energy, the work function, extract the binding energy in a solid and the crystal momentum, so the momentum of the electron inside. In practice, an image like this can be directly compared to calculations of electronic structure you would do by density functional theory. And as we went in and did these experiments, so the first step is, of course, the instrumentation. There is instrumentation around the world. Synchrotrons are a natural place to do this, because you can tune the photon energy over, from the XUV, say, into the X-ray. So you need high enough photon energy to the experiment. So these are beam lines that we build at the Canadian Light Source for angle resolved photon emission or even resonant X-ray. Eduardo here has made big use of both facilities. And we also have facilities, of course, of UBC in-house. And so these are the kind of places where we do the experiment. And then what we look at is, going back to the phase diagram, is now the Fermi surface. Fermi surface, we can start on this side of the phase diagram where you have more conventional metallic behavior. And before I showed you, the Fermi surface is basically a contour that can close, separates occupied from unoccupied states. In this case, what I'm showing here is a Fermi surface over one unit of symmetry in momentum space. It's called the Brillouin zone. But if you imagine of replicating this Brillouin zone everywhere, here is where your closed contour would be. In fact, this system has two Fermi surfaces, one here and one bigger. And okay, this is what the conventional picture tells us about it. The Cooper pairs giving rise to superconductivity are coming out of those electrons along the Fermi surface. And as you move down towards the underdome side, the Fermi surface breaks down in disconnected arcs. They are called Fermi arcs. And so that's really the transition from conventional behavior into unconventional behavior. And it's that interplay that really we believe would give rise to the high temperature superconductivity. And I'd like to, as a specific aspect here, to note that you see the dome, which has this particular shape, has an anomaly here. And that anomaly has now been associated with a tendency of electrons, valence electrons, to charge order in these materials, which is what Eduardo has made a major breakthrough and has contributed a major breakthrough to in his work as a student and postdoc, and even now. So basically, this is now what we, really the picture that we have for these materials. And that also relates to the superconducting gap. And that's the last part I'd like to show you about the past, where again, here is an image of this Fermi surface. And if you want to look at the pairing symmetry with these techniques, what you can do, you now already explained that the pairing symmetry would have this dx squares minus y squared shape. So large gaps along two perpendicular directions, zero gap or zero pairing along the other ones. Experimentally, what it means to do an experiment. Here is the chemical potential. Electrons should be present up to there. If you look here in the middle, you see a peak located exactly the chemical potential. But as you move along this Fermi surface here, So you move away from this peak. The peak doesn't stay at the chemical potential, which would be the behavior for a normal metal, but actually pulls back. It pulls away from the chemical potential. The pulling away is what we call the gap, and is direct measure of the pairing. If we plot the position of this peak as a function of this momentum direction, which is along here, you can see 0, that's the node right in the middle. And as you move away, the gap gets larger to a maximum value here at the zone boundary. So this is now really the magnitude of the pairing interaction in high temperature superconductors. And that's what we call the D wave gap. And the node, of course, in this experiment is limited, being able to see by resolution, but the microwave experiment really proved the gap goes exactly to 0 at that particular point. That's it for the past. That's where we started from. And, cuprates have been extensively studied over the years. Now the question is, what can you do? What is new in superconductivity and in high temperature superconductivity? So that's what I'm going to talk about today at this particular point. Before we saw a Time magazine cover that was about high TCs, the next big surprise came about twisted bilayer graphene, and here now made the New York Times. And what you're seeing here is a structure built of 2 monolayer graphene layers. These 2 monolayer graphene layers here have been stacked on top of each other with a small twist angle. You can see here the misalignment at this particular angle. And as you do that, you see a pattern that emerges, from the overlap of the 2 structures, and this is what is called a moiré pattern. Basically, you start off with a symmetry unit, which is very small, is capturing basically an hexagon of this graphene layer. But as you make those, you can see that now the modulation is on a much bigger spatial scale. This is work that comes out of the MIT group of Pablo Herrero, and really has raised immense attention in the last few years. And the reason is that as you start twisting and moving these things, you can really engineer the electronic structure of these materials. This material is graphene. Graphene is known for this hexagonal type symmetry with Dirac cones, so these linear dispersive bands, energy versus momentum for the electrons, touching each other at the Dirac point with the chemical potential located exactly there. But now as you take 2 of these layers, you put them on top of each other, the Dirac cone would overlap, but as you start twisting, they move away from each other, as in this case. And now if you allow these layers to interact, if there is a finite interaction between the layers, this is going to lead to a reorganization of electronic structure. It's a bit like having a molecule, and all of a sudden the 2 atoms are close enough and they form bonding antibonding levels, no longer 2 degenerate level. And so what happens next is, instead of having 2 Dirac cones located at different places, all of a sudden you get a very narrow band where they touch. And so that narrow band now is very interesting, because the narrow band means that you have increased your electron density in momentum space by making them very much confined in energy. So now graphene is a non-interacting system, but as you increase the electron density, even a small interaction becomes significant, and this material becomes a superconductor. So it's really, almost electronic engineering, engineering electronic structure at its best, just simply changing the angle. And you can see that in the experiment, what Pablo's group has done is make devices out of the twisted bilayer graphene. Basically, you have contacts, you can bias the sample, you can measure currents. And here again, you see resistance versus temperature for one such device. Of course, these are exfoliated graphene, so they're small devices. 5 micron is the scale you see there. And what you can see is the resistance that comes down again, metallic behavior, and then eventually goes superconducting. Interesting is to notice the difference between the 2 is a small change in the twist angle. So extreme sensitivity to the twist angle basically requires high precision in making it, but really allows you fine-tuning the superconducting properties. And again, graphene by itself would be not superconducting at all. So superconductivity really comes out of this deliberate stacking and twisting. Of course, in principle, that is already in a form of device. That's already interesting in itself. But really, when it comes to the fundamental physics, it's interesting to compare the graphene phase diagram to the cuprate phase diagram. And here is the phase diagram we saw before: superconductivity, antiferromagnetism, This is basically an insulator where correlation between electrons are very important. And if you look at the graphene case, where you tune the electron density now by a bias voltage, excuse me, by a bias voltage, not by, let's say, chemistry, but a bias voltage, you can see superconductivity, you can see more conventional metallic behavior. And here in the middle, in red, you see an insulator and a correlated insulator. Now, what is interesting is here that you see these are phase diagram that we call hole dope side of a phase diagram. We put holes into it, but we can also dope an insulating cuprate with electrons and go into the other side. And if we do so, you actually find something which is very similar. It's almost a mirror image with some difference in, you know, the antiferromagnetism being stronger, superconductivity being weaker. But that's exactly what you're going to see. And what is really remarkable is if you do the same on graphene, and if you dope now at lower carrier densities, you see again superconductivity, basically two superconducting domes, like here, separated by a MOT or correlated insulator. So that's really where the two systems, even though they live at very different temperature scales, 100 Kelvin, 1 Kelvin, they behave very similar. And this is really having to do with interactions and, you know, very strong interaction in the case of the cuprates, and here interactions have become remarkable once you engineer the band structure. Well, after this, another major discovery or breakthrough was obtained. This is, yes, please.
I assume that in the cuprates, as you lower temperature, the antiferromagnetic phase resistance is very, very high.
Is extremely high, yeah.
On this graphene, it becomes small resistance at the temperature in what's supposed to be the insulator. Like between the two superconducting.
Well, so
if you know, I mean, I know it's not your work.
well, first of all, the scales are not comparable in terms. Nowadays, this particular phase diagram shows additional complexity. I think it depends a lot on the quality of the device you obtain. I think in the most recent so while this comparison looks very, very intriguing, in the most recent version of this phase diagram, you actually see that you get additional insulating phases. So I think you now can achieve clean insulating behavior here, but then you also see other differences, which are additional insulating phases at different doping levels. So there is quite a bit of complexity now coming out of here. One key difference is, as in the early days, there was a lot of chemistry work done in optimizing the material. Here, there is a lot of device work in optimizing, fabrication work in optimizing the device. And the other thing is really the energy scale are different. So what is here described as a mod insulating state is certainly not as strong an insulator as that. That's for sure. The next breakthrough that brings us back to cuprates is the following. So we're seeing graphene. I think you're familiar with graphite. Exfoliates very easily. That's why you can use a pen and write on paper, because you leave behind parts of graphite. But if you look at cuprates, and here is one particular system, the bismuth, strontium, calcium, copper oxidoside, the key element are these copper oxygen planes here. It's a nice square copper oxygen plane, copper oxygen 2. So one copper atom and 4 oxygens around. And those two planes is where superconductivity takes place. And then in between here, they are separated with 2 blocks by what we call the van der Waals gap, or rock salt type layer. This is bismuth oxygen. So what you can do here, you can cleave the material very easily. So it really breaks at this very weak bond, to the point that you can make a single block like this. You can isolate a single block like that. And here you see the resistance versus temperature for 2 systems. One is the bulk superconductor, and the other one is the monolayer. And then you can see they're exactly the same. This is a major achievement as far as fabricating a single monolayer superconductor, the single block. It's extremely difficult to get it and not damage it, not lose oxygen that will kill superconductivity. But what is remarkable is how the demonstration that superconductivity is really 2-dimensional in these materials. We already knew that to a very high degree, but this is very visual and practical demonstration of this fact. Superconductivity lives in the single layer in cuprates. Now, if you can do that, then the question naturally arises, could you stack and twist this material versus twisting graphite? What would happen then? There's a question that my colleague Marcel Francis asked. So the idea is very simple. You take 2 of these layers now. Each of them has a D-wave gap, a D-wave pairing symmetry, Now you rotate them by 45 degrees, and you align the nodes of one layer with the direction where the gap is maximum in the layer below. And what would happen then? And the question is, well, if there is an interaction, you can now give rise to a completely different kind of superconductors, an even more exotic superconductor. So that's exactly what was done. And here you see the idea. So monolayer cuprate, the pairing symmetry is described dx squared minus y squared. It's D wave in shape. You take a second layer into the picture, you move and overlap the two, and now let's say you turn on the interaction. And here is what the change is. Instead of dx squared minus y squared, you go to a system, and you can show that theoretically in various ways, which now has an additional component, I dxy. What it means in practice is before you had a superconductor with nodes along the diagonal, but now because there is interaction, the pairing is non-zero everywhere. Okay, that's just a quantitative statement like that, but in fact, is not. This particular material would exhibit a spontaneous breaking of time reversal symmetry, and in fact becomes a topological superconductor, which means that you have excitation in the system, which are topologically protected. From a practical point of view, topological superconductors is something that people are working on actively because they could become the basis for topological devices. And we'll see a little bit of that in a moment. But pretty much when people think about quantum computation and what is a system that provides you robust coherence for quantum computation, and they think of superconductor, well, a topological superconductor would have an added degree of protection in that sense. Please.
So if the interlayer coupling is so weak that the superconducting property remains the same in the monolayer, what would be the energy scale that due to this interlayer coupling induced I term?
Okay, so the question is, sorry, I should repeat the questions for the people online. So the question basically is, what about, is the interlayer coupling strong enough to give you something like that or not? Basically, if there is no interlayer coupling, you just get two pieces of superconductor with opposite, well, with a different orientation for a superconducting gap, and nothing happens. So if you look at the full range or in parameter space, there is an ideal range of interaction that you need. You can have, as a function of that parameter, that is a key parameter in the modeling. As a function of that, you have all kinds of phases. So the question really was for us, do we have a realistic and significant value for that parameter? So what we did was and did a calculation of it. So we can use density functional theory. So that's where we go back and forth when you talk about material by design. Here is a concept. Can we make it? Now we can go in with a computational approach and see where are we? And then eventually the question is, can you actually fabricate this? So the calculation is now done, assuming that we can break the material here. We know we can. We bring them back in the calculation. We rotate by 45 degrees. And then here we look at the total energy of this bilayer and ask, where does the total energy reach a minimum? And the minimum is here for 12.7 angstrom between the middle of these layers. 12.7 angstrom between the two layers, or so say. And then we can go and look at this quantity. This quantity is a splitting in the band structure, but basically what it means is a splitting between electronic levels. So the splitting, if the two layers are very close, the splitting between the electronic levels in the structure becomes very large. And so now we go and look at the value where we are, 12.7, and this is what defines the interaction. And now the question is, and so it happens that that parameter is right in the range that you need to have a dx squared minus y squared plus I dxy superconductor. So it's the right parameter value in order to get a topological superconductor in this case. Yes.
So what breaks the time reversal symmetry in this setup?
Is really the symmetry of the order parameter you are able to create. In this case, that does it. So you need that interaction between the two order parameters, between those two.
Because the question that you stack two layers, the system has time reversal symmetry. So d plus I dy comes out of spontaneous time reversal.
Right, yeah, because there are currents running now. So definitely when it twist, plus, so what's missing is that the D wave is plus, plus, minus, minus. So delta is a different sign. So you can twist to some extent.
then plus may be somewhat above minus.
Right. So
It's some kind of a texture in a mental space. At least that's what was theory prediction.
so you're going to see that exact situation where, you know, the positive phase will overlap with the negative phase in the next slide. But basically, you're inducing that by really the interaction between those two. If you didn't have that,
That's large enough to, to overcome what you want. So basically, it must be because
Yes.
Anyway. So what is it? I just don't remember. What is the size of the unit cell
of BISCO,
of this? Yeah.
basically, this is, well, it's something like 20 angstrom, I forget, 30. So basically, this is 12, 13. Yeah.
Compare this copper distance. I mean,
You mean this one, huh? This one,
are they really on top of each other, or are they separated by some?
they're separated by 12.7 angstrom. So that's where you find the minimum in total energy for the system.
Copper plates are somewhere in the individual plate.
So, okay, a couple,
Out the top of the original.
yeah.
Right.
Well, a couple of statements here. First of all, this is a bilayer BISCO. Okay, so this is just an added complication. This calculation has been done for single layer BISCO. Okay, so layer BISCO to 201, just as a model calculation. And so basically, imagine this unit to be a single copper oxygen layer. And then the distance, the constant, the key is the distance between one and with a rotation. And it's very comparable. It's very comparable to what you have in the crystal, but now it's rotated. And the question is, all you do, the distance is basically the same. You rotate it and you're asking, is it stable? And what is the distance between the layer? And the layer it's very comparable to what you have in the crystal itself.
I'm sure it's comparable, but because of atomic physics, comparable, but I hope larger than.
Well, you can see it in the inset. You see the unshifted and shifted. They basically have the same minimum within a tenth.
I see. So that's basically based on.
Very simple.
Yeah, so you're right that you should not expect a difference, really, right? So the question is does that do very much to the structure? It's stable and total energy is comparable.
So your point is simply you want to rotate without changing the distance between the layers.
Ideally, and then extract what is now you're also, there's something else going on though. You're changing the Hopf path, right? So the hopping path is now changing between the two layers, right? And so the question is not so much this one, this is fine. Question is, okay, what happens to the interlayer interaction? Which turns out to be a little bit smaller in the undistorted structure, but not remarkably small. So perhaps that would have been a better comparison. Instead of showing this one, show what happened to the. Okay, well, so this is, of course, the prediction now, and how do you make it? Well, the idea is to do pretty much the same that you do in bilayer graphene. So you have to have a way of working with your inert atmosphere. Now you have a polymer here in blue holding a bismuth crystal, a bismuth cuprate. Here you have a silicon oxide substrate. And what you do, you approach one with the other. You approach the crystal onto a substrate that sticks to it. You pull back, and then you rotate your substrate by 45 degrees. The advantage here is that it's easier to do 45 degrees versus 1.1. That was the case of graphene. And so you come back down. And here is an image, an optical image of what we obtained. Now, the key, though, and this is something that was really developed by Philip Kim, is it's very easy to degrade the surface, to lose oxygen through the surface during this process, and have even reconstruction at the surface. So what was developed was now an approach where the samples are being prepared at low temperature so that as you do the stacking and lifting, the sample is cold. And in fact, now this has been pushed down to about 90 or 100 centigrade. And of course, it has to be done in a glove box with very low humidity. Otherwise, you start getting water onto it and becomes a real problem. Now, as far as achievement, we are working on this at UBC. The idea is now to go and do spectroscopy on this to look at, for instance, the gap. Is the gap evolving from the D wave gap, so anisotropic, to something which is non-vanishing everywhere? And that's basically where you need an institute. So that's basically the point I want to make. This particular project relies on a concept. This was work on Marcel Franz. This was work on Andrea. And The material, of course, making the material is a big team effort. Actually, the crystals were made by me back in the days, but the person who's really going the stacking and so on is Ziliang himself. Ziliang is the leader of young leader of an optics group at UBC. Then we go for experiments like the time resolve work, the angle resolve work, where we look at the symmetry of the order parameter. That would be what we do on this system. But then eventually you go to the devices. That really is the goal. The goal is to go into topological devices. And so that's where Josh Falk, our device expert, comes in. Now, as far as the particular work, I'd like to announce, one major breakthrough was obtained at Christmas time. Just before Christmas, this paper was published. This is led by Philip Kim and Marcel Franz. At that time, Philip Kim was working on this already, and then saw the paper, our paper coming out, and so immediately got into it and got interested in what we were proposing there. And here you see a device made of two stacks of two Bisco crystal rotated by 40 gravity, but now with all of the contacts and so on. And here you see a TEM image, which is really important, where you have one crystal and the second crystal. You see the structures are a little bit different for details of the structure of these materials, but then you can see a very clean interface between the two. And that's where the action really is. You need a very clean interface. Now here for the experts, it gets a little complicated, but here you have a function of angles. 45 degrees being one layer and the other are really opposite by 45 degrees. What you're looking here is the tunneling current between the two layers, and is a superconducting tunneling current. And if the linear term of that will go to zero, exactly 45 degrees. So the linear term in the tunneling current, the Josephson current, will go to zero at 45 degrees. And that's what one expects. And so this is the proof that the junction that is being made there is a superconducting junction between, and what you're seeing is incoherent tunneling between two D-wave superconductors. However, things get very interesting in this region, where basically the leading term, the linear term is going to zero. Now you can look at nonlinear terms. And as you look at nonlinear terms, now again as a function of a twist angle, you can start looking at what is called basically a superconducting diode effect. And really you have to be in a region where the linear term is going to zero, so away from zero, approaching 45. And so, but also you cannot go to 45, otherwise the superconducting diode effect also will go to zero. So I want to show that, basically attract your attention to the fact that you have no response here, no response there, but there is a region here in the middle where now you can see that the signal for what is a diode current, a diode effect, goes away from zero. And basically this is this area, this particular signal, it's a very delicate and weak signal that demonstrated you have been able to have basically a topological superconductor that breaks time reversibility. So it's really coming from that. And basically this is a demonstration that you can use these kind of devices for topological functionalities. I think we are almost at the end of the talk. We have some delays, but I'll try to keep it on time. And so future, what is the future? We've gone from the discovery to, really looking at making devices and pushing topological devices, for instance, superconductivity to really high temperatures. But what about the many body states of these systems? And so that's where I'd like to bring a couple of examples where I think that new spectroscopic approaches can really help. So there is a switch now. Before I showed you angle resolve for the emission, that's what my group does. Oops, sorry. These days, together with David Jones, also faculty member in the Institute, we have worked on time resolve for the emission. Basically, the idea is using lasers as light sources and not synchrotrons, having very short pulses, femtoseconds, 100 femtosecond pulses, and then having one pulse that goes and excites the electron system in your material, and the second pulse that comes and probes it. And you can use it in two ways. One is to learn about the properties of a material. The other one is actually to drive optically the system into a new state of matter. And so that is a challenging experiment because in order to do photo emission, you need photons with an energy of above at least 4 electron volt, but in practice, 6 eV and higher, basically well into the UV or even better into the extreme UV to be able to scan all the momentum space. And so that's where David Jones' group comes in. What you see here is a blue UV photon coming onto a sample, but this UV photon is being generated by high harmonic generation in a gas jet. And the challenge there is to be able to come in with a very short pulse and yet have a decent energy resolution. And these two quantities are related by Heisenberg. And so then you have to really be able to fine tune both of them to get the best of the two. So basically we're pushing, just in terms of numbers, for something like 200 femtosecond temporal resolution and 15, 20 milli-electron volt energy resolution. So that's really the challenge here. And this is done based on a technique which is basically a passive enhancement cavity. Is a way of doing high repetition rate generation of photons with very low peak powers. And then you go select the particular harmonics you want to have. And at the same time, you have now an infrared beam that comes in, and the two of them you can control with a delay, and this, so that you can see what happens and take a movie of your electron excitations into the material. Now, as an example of what can be done, just very simple, very, very simple is, you can do things like looking at graphene. You come in with a pulse that excites electron from the lower part of a Dirac cone in the upper part, and then you can watch this electron relax. They can relax through electron-electron scattering coming down this cone, but they can also interact with the lattice. And electron-phonon scattering is a critical parameter, determines the performance of electronics, determines superconductivity in some cases. So really is a quantity of interest, but it's really hard to get as a number. And so we know that over time, this electron will also scatter emitting a phonon and be basically dropping down to an energy corresponding to the phonon energy. So here is what an experiment would look like if you did it time resolved. At t equals 0, let's say pump and probe are superimposed. You're going to photoemit and from the occupied part of the cone, but you're also going to see intensity, bless you, up there at the where you have excited them optically, right here. But if you wait some time, and the time is the characteristic scattering time for electron phonon scattering, well, then you're going to see some of the intensity trickling down exactly by the frequency of the phone. And so if you now can measure this time by following the evolution of the intensity, you can use a very simple relation that connects the electron phonon scattering time to the electron phonon matrix element or the electron phonon coupling directly, where here is lambda is the coupling between electrons and phonons, n is the electronic density, omega is the frequency of the phone. So this is one case where you can use now a very advanced technique to extract a very microscopic parameter, lambda or g, the matrix element, directly just by watching how the intensity is evolving into the experiment. Now, I don't want to delay this, but tomorrow is something that we'll discuss this in great detail. So here is a spectrum up here, very little, you can see a tail of electrons relaxing down to the chemical potential. You see some structure in here. If I subtract the tail, these in blue are two optically allowed transition in graphite, not graphene, but it's very similar to graphite. And then there is a peak that you see at an energy which corresponds exactly to the energy of a phonon. And if you follow this in time, so this is the delay between pump and probe, well, you're going to see that for the blue transition, the optical transition, the maximum is taking place where pump and probe are coincident. You're directly promoting electrons into the unoccupied side. However, if you wait long enough, there is another peak coming up, and this is a maximum here at about 50 femtosecond or so later. This is this particular peak, is the electron that falls down by emitting a phonon. And so by following this, we can extract in detail, by modeling this data with rate equations, we can extract the electron phonon scattering time, 170 femtosecond, and from that, we can extract G, which is measure 0.05 electron volt square, and we can also calculate and 0.04, and you see how in good agreement these are for a simple system like graphite. So that's one way to show how new techniques really can give you direct access to some of the fundamental quantities. And last, just two examples. And if you want to take it to the next step, this is what I will talk about tomorrow. You can use the same technique. This is actually work done by Fabio Boschini, now a faculty member in Montreal, and Eduardo, when they both were as postdocs in my group. And what you can see here is basically the superconducting gap of the cuprate And the sharp peaks are before the pump comes in, and then the pump comes in, and what you see is a redistribution of spectral weight here. And what we can conclude is that the peaks are not really moving into this, but really it's their width that gets broadened out. And so width means lifetime of excitation. So by pumping, we suppress superconductivity by killing the lifetime into the system. And so what we concluded from this work is that we quench superconductivity not by reducing the pairing, by reducing the phase coherence of the overall condensate. So affecting the phase coherence versus the pairing strength. And another way of using these approaches, which is very interesting, this is highly debated, but really very interesting, is done by Andrea Cavalieri, Max Planck Hamburg, and is that of coming in again on these superconductors, now pump them with an energy which is resonating with some of the optical phonons in the system, so the lattice vibration. And what they believe they see an enhancement of superconductivity from these numbers almost all the way to room temperature. So this is what would be light-induced superconductivity. So it's another big branch of work in a quantum material direction where you really drive new states of matter optically or in cavities. So there is really one range of possibility. Okay, and as for the very last, the idea is what we're building on, working on building on right now is a new project, 2-electron photo emission. It was funded a few years ago, again involving people from Max Planck, like Kaiser and Keimer, and a number of people from, of course, UBC and Canada. And the idea is in photo emission, we come in with a single electron, single photon, remove an electron. And unfortunately, we're removing from Cooper pairs, so the many body state for superconductivity, but we lose any information about the inner structure of this wave function. That's basically all we can get to. And so the dream would be to come in with an energetic enough photon so that you could remove both electrons and then measure them at 2 detectors simultaneously in coincidence. And what you should expect is if the Cooper pair is a total momentum of 0, the 2 electrons should come out with a plus and minus k, so opposite angles. So the idea is to go around with 2 detectors and collect the coincidence signal and really look at the angular structure of that signal and eventually look at the inner structure of that many body wave function, say. And so really that's what we're trying to do. So this would be Cooper pair spectroscopy as opposed to single particle or single electron spectroscopy. And I'd like to mention that this is also very related to work done by Seamus Davis in doing scanning tunneling microscopy, and instead of tunneling single electron, again, tunneling Cooper pairs. So this is called Josephson tunneling, again, similar to what you've seen. So all kinds of new spectroscopic approaches, they really allow you to look at the microscopic parameters and the many body structure of these materials. Finally, all I showed you today was one of the areas of work in QMI in our institute. Basically, was superconductivity. The operation of the institute is organized strategically around 3 grand challenges. That's when we did our strategic exercise. One has to do with engineering exotic phases in 2-dimensional materials, and the superconductivity I showed fits in there. Of course, there is much more than just superconductivity. There is magnetism and other properties. 2 others I'd like to mention are atomistic approach to the as a way of eliciting new properties. An atomistic approach really means putting together materials, looking at those atomic-like interaction, like Coulomb interaction on site, magnetism, spin orbit coupling, coupling between all these different energy scales. And so that's in a big area with a lot of design work of materials and fabrication. And finally, there is another one which really relates to quantum information and quantum computation. So using existing approaches, quantum computing approaches, to look at materials, have a better understanding of materials, use them to design better materials, and eventually use those materials as a platform for quantum technology and quantum computation. And with this, I'd like to thank you all for your attention.
Thank you, Andrea. We're open for questions.
Yes, I think it's a wonderful talk. You mentioned at the very end as a appetizer the electron phonon interaction and this lambda Q. I think actually what you had in graph some average. Yeah. So the question is what is the resolution? I mean, if it's an Einstein mode as you stay here, then I understand it's just one frequency. But
yeah,
there are lots of modes and they
there are a lot of modes and a lot of electrons. So in principle, in this particular case, we claim that we are able to look at the specific electronic state with a given K and look at a specific Q. And this is allowed by effectively by, well, having resolution in momentum, but also the fact that the band structure is quite simple. It's a very simple electronic structure. So the amount of phase space is not a lot. There are two, first of all, there are Einstein modes. And there are two possible ones. One is a gamma mode, and the other one, which basically would be a vertical transition, and the other one is a K mode, and they have different energies. So the combination of where you see the scattering taking place in momentum and what is the energy that you see allows you to conclude whether you're looking at one versus the other.
But if you fix both K and Q, then it should be, I mean, theoretically, it should be just delta function peak, right? No?
Oh yeah, but
Yeah. So where's the width comes from?
Well, the width comes from now we have resolution of the order of 20 femtosecond and 20 MeV, right? That is, you're basically, this is sort of a challenge where depending on what you're after, you may or may not have that resolution, right? And not only that, you have, in fact, you have two optically allowed transition. Both of them will, in fact, in the system, we are free optical allowed transition, but one we had missed is above here and we didn't measure. So, but we did, they're free optical allowed transition. All of them will see interaction intensity coming down through electron-electron scattering, which gives you the tail and electron phonon. So you get all these peaks. So in the actual rate equation that we use to analyze the data, we include all these peaks. So it's a combination of quite a few features superimposing with each other and then limiting resolution.
Thank you.
And just experimentally for, here you're looking at very weak signal. These signals are about 4 orders of magnitude weaker than what you have at the chemical potential. So we are doing photon emission not from the occupied part. We are promoting electrons above. They have a limited lifetime, 50 femtosecond for what concerns the electron scattering and 170 for what is the electron phonon scattering. So really the lifetime is very short up here. Still you can see that because you're working on a reasonably flat background and you have very high signal to noise. But yeah, resolutions are your limit. You could push the time resolution, then you lose the energy, or you can push the energy resolution, you lose the time. So ideally what we're trying to do with our system now is to have it such that you can, in real time, tune between higher energy versus higher temporal, which is a dream as well. But this is something we're working on. Yes.
Thanks for the nice talk. I wanted to ask about the twisted bilayer graphene example that you gave. So you showed how, like, as a function of the twist angle, you can sort of change the band structure a little bit. You showed a diagram that shows the Dirac points moving relative to each other. And so my question is, do you expect the superconductivity that emerges at the interface to care about the presence of extra Dirac points or extra locations where you have Van Hove singularities? And maybe a follow-up to that, could that be relevant at all in your twisted cuprate system?
So the two systems in a way are very different. The twisted cuprate does not give rise to let's say the key effect is not associated with the moire superstructure. So it's not so it's basically having to do really with the alignment of these superconducting gaps. Okay. In this case, the details are really dependent on the moire superstructure itself. So the band engineering that we see here, the details of this, this is actually a movie that Pablo always shows, where you can see as you change the angle, there's a lot of action right here. So that's extremely dependent on that. It's extremely dependent on that, and I guess in an ideal system, this would be something that I would put a lot of trust in terms of being able to predicting ability. The problem is when you make devices, there is all kind of effects that come in, including bubbles that form here. The angle is not exactly homogeneous everywhere, so those details really play a big role. Those details play a big role. If the system was ideal and didn't have all these imperfection and additional local interactions, I would say that given that the graphene is very well described by density functional theory, I would put a very strong level of trust in here. At this stage, I think that deviations from that are really coming from the challenge of making the devices. And maybe related to this, when we go to the cuprates, I'd like to highlight one aspect in the experiment done by Philip Kim, which is each data point here is a different device. Each data point is a different device like this one, where you exfoliate at -100 centigrade in some inert atmosphere. You bring the samples together with the control angle, and you go from the 0, so on top of each other, all the way to 45 degrees and past that. And so each of them, and then you go put the contacts on. So it's a major tour de force experimentally. And so these devices, you can see there is, especially here, in terms of error bars and so on, distribution is a super challenging experiment.
Anyone have any more questions? Just perhaps the last one from you.
So, and maybe if I can add here for the expert, if you look here, you see this funny modulation. The layers are not flat at the top. And that is because bismuth strontium copper oxide is the bismuth oxygen layer, which is a little bit, bismuth is a big atom, so gives rise to some mismatch and so some modulation along one particular direction. So you can see it in one end or the other, and then when you put them together, that certainly can play a role too. It's bringing in now, before it was asked, a structural asymmetry, which is pre-existing your pairing the matching of the superconducting gap. So those details for sure play a role.
Thanks for the great talk. I have a quick question regarding the electron phonon coupling vertex extraction. So I guess the key here is really to measure tau q. Is that a single particle lifetime or
measure
tau q?
Yes.
Is that a single particle lifetime or population lifetime? And insofar as I understood, these two are very different quantities. And I guess I'm also probably missing a higher level conceptual advantage of this technique compared to directly measuring the self-energy of, say, particular phonon in Q space with inelastic neutron or X-ray scattering.
Okay, so the idea is okay. So this is the basically look at the integrated intensity of these peaks, right? Look at the integrated intensity of these peaks and see how it changes with time. So basically, this is the result of the process of a single particle, single electron scattering with single photon.
So that's a population lifetime.
It's a population. It's
I see.
So basically, what you get out of that, and again in that we have two scattering processes that we include. One is the electron-electron, and the other one is electron-phonon. And then by doing the full analysis of these intensities, the lines that you see going through, they're not guides to the eye. They are really the result of rate equation to the overall spectrum over time.
Okay.
Like that's one thing. Now, when you're comparing your neutron or photon emission or scattering versus this, it's basically the question that was asked before. What are the advantages and disadvantages of each probe? So ideally, you would like, electron phonon scattering will depend on the K of the electron. So which state are you looking at, and to which state are you coupling, and with which which phonon, of course, as well. And so then the question is really, if you look at the different techniques that will give you, in some cases, something that is specific for a Q, integrated over all possible momenta for the electrons, or specific for a K, integrated over all possible Qs for the phonon, even for a single branch, say. In this particular case, so it works that by having a knowledge of the band structure, having a knowledge of what are the optically allowed transitions that you can use, you can position yourself and now extract that information for a specific K and specific Q. In principle, one could change the, sorry, I don't have it here. One could change the excitation energy to scan along that cone and now give you, as I scan along the cone, also not only the K changes, also the Q changes. And so that's basically what we would like to do. And this particular experiment was done with the fundamental photon energy we get out of our oscillator Now we have an OPA, so an optical parameter amplifier, so we can change the photon energy also for the pump. And the idea is to really do that. So I think all of these techniques are great, and they all provide you one complementary view on the problem. This particular case works extremely well because of a limited band structure. If you were to go to a much complicated band structure, then it gets more challenging.
Okay, I think we are. So let's think of it once more.
Thank you.
No, I just,